Hello everyone, happy to see you again and I hope everyone is doing well. And today we are going to continue with the Hadoop ecosystem. More specifically, we are going to talk about Hadoop architecture main components, HDFS, MapReduce, and Yarn. Throughout this presentation, we are going to follow the following plan. First of all, we are going to discuss Hadoop as a solution. Afterwards, we will discuss HDFS architecture. Subsequently, we will present the MapReduce mechanism and we will finish with Yarn. In fact, Hadoop framework application works in an environment that provides distributed storage and computation across clusters of computers. We can name two principal layers that contribute the most to its functionality. MapReduce for processing and computation layer, and HDFS for storage layer. We can see in this slide that HDFS HDFS is distributed storage system that supports petabytes of data. So each file of data will be divided into many data blocks. Furthermore, it is endowed with an error tolerance mechanism that is ensured due to data replication. So, what is Hadoop cluster and why it is efficient? In fact, Hadoop cluster is defined as a collection of nodes that are networked together in order to perform parallel computation on a big data sets. Hence, Hadoop clusters are designed to store and analyze massive amounts of data in distributed environment. We can see in this slide that Hadoop clusters architecture, and it is apparent that the large Hadoop cluster contains many racks. There are in each rack lots of data nodes available, and they are supervised by a name node which is called the master. In this architecture of master-slave, therefore we can define the main components of as follows. We have the name node, which is also known as the master. Name node only stores the metadata on HDFS. It is a directory tree that contains all the metadata, that contains all the files in this file system, and it tracks all the files across the clusters. The nodes other than the name node are called the data nodes. The data nodes are responsible for storing the actual data in HDFS. We can summarize this all in this slide. So we have each data file will be divided into many data blocks, and these blocks this data will be stored in these blocks. We have the name node store all the metadata that are related to these blocks. This metadata includes file names, file permissions, block IDs, block locations, and the number of replicates. So if client wants to request a specific block, it would request the name node for the metadata. So after getting this metadata, the client would access the data block directly. So from what precedes, let's define the responsibility of each component in our architecture. We have the name node. The name node is responsible for monitoring and managing the data nodes. It is responsible for the namespace of the file system, and it captures all the changes to metadata, such as deleting, creating, renaming the files in the edit logs. So it receives also the heartbeat signals from the data nodes every 3 seconds, and it performs file systems operations such as opening, closing files, and directories. Now we move to the data nodes. Data node runs on slave machine. So a typical HDFS cluster has several data nodes. In fact, data nodes store data blocks or actual data in data blocks. Data nodes perform block creation, replication, and deletion according to name node instructions. So every 3 seconds, by default, name node sends a heartbeat to name node in order to report the HDFS system integrity. And the third component, which is the secondary name node, actually the secondary name node performs maintenance tasks on the behalf of the name node. More precisely, the secondary name node updates the FS image file at regular intervals by including the contents of edit logs. So the merged file will be a new FS image. So the name node will download periodically this file in order to actualize the data. We can see in this architecture that the secondary name node works as a helper node to the name node. To be precise, secondary name node, the whole purpose is to have a checkpoint in HDFS. Now we move to MapReduce. MapReduce is undoubtedly based on parallel programming paradigm. This latter aims at generalizing existing approaches in order to produce a single approach that is applicable to all problems. It is based on functional languages, and its origin goes back to 2004, when Google published a paper called MapReduce, Simplified Data Processing on Large Clusters. The problem of MapReduce 1 is the non-separation of resource management tasks from the ones of MapReduce. The predefinition of slots also triggered problems. Therefore, the version 2 of MapReduce overcame all these problems by separating resource management tasks from the ones of MapReduce. No predefined slots concept is existing. The nodes have their own resources and they are allocated to on-demand application. There was a new definition of new daemons, so most of the job trackers features were moved to the application master. A cluster could have several application master, and this version supported both MapReduce and non-MapReduce application. Now we move to MapReduce different phases. So in order to MapReduce to take place, there are many steps that are required. First of all, this phase split. This phase allows to divide the input data into parallel streams in order to be supplied to compute nodes. The read phase allows data streams to be broken into separate units to be processed. So a text file, in the text file, a line will be considered as a unit of processing. The third phase, which is map, allows to apply to each unit a transformation process, whose result will be stored in key value pairs. The reduction phase, which is an optional component that applies an early reduction processing for optimization purposes. And finally, the write phase allows to write the results of the processing into separate result files. Now let's see an example of MapReduce word count job. So we have here an input text file that consists of many lines. So each line will be considered as unit to be processed. So the map phase allows us to guess the first form of key value pairs. We have dir1, bear1, etc. After the shuffling phase, the reduction phase is applied, and it will allow us to guess the key value pairs that correspond to each word and its occurrence content number. So we have bear occurred two times, we have car occurred 3 times, and so on. Finally, the result will be stored in separate files. Now we move to Yarn, which is the resource manager. So Yarn stands for yet another resource negotiator. The fundamental idea of Yarn is the separation between the functionalities of resource management and job scheduling or monitoring by providing separate daemon for each one. So we have the daemons that are such as the global resource manager, and we have the application master. So we can summarize all the involved components as follows. We have the resource manager, the node manager, the containers, and application master. Each of these daemons is defined in the shown architecture. So the resource manager is executed on the master node. It works as a global resource scheduler. It allows resource arbitration between multiple applications. We have the node manager. It runs on slave nodes, and it communicates with the resource manager, usually to ask for resources. We have the containers. The containers are created by resource manager on demand. They represent an allocated resource in the cluster. And we have the application master. There is only one per application, and it runs on a container. It requires multiple containers in order to perform an application tasks. Now let's see an example of the word count job, MapReduce job, in order to be done in our Yarn architecture. So first of all, the client submits the word count job to be processed. So the resource manager allocates the first container for the application master to be executed. The resource manager launches the application master on the node manager, and the application master and the application master requests for resources in order to execute the MapReduce job. So the resource manager will give it the required resources as containers. So the MapReduce will supervise all the MapReduce jobs that are executed on containers. Each of these containers will notify their status to the application master, and when the job is done, the application master will send a notification to the resource manager, the finished notification to the resource manager that the work is done. Now we have come to the end of this course. So we have seen throughout this presentation the importance of HDFS and how it was the answer for the data storage challenges. In fact, it is a promising solution with a low cost and fault tolerance mechanism for unstructured and huge amounts of data. Furthermore, MapReduce appeared to be a simple model for parallel programming, endowed with the fault tolerance authentication and security insurance. Now, if you have any questions, feel free to put it in the comment section, and we will do our best to reply to it as soon as possible. Thank you for your attention.